Okay, now. So we're going to talk about torque, not in terms of radius cross force that creates torque, or I times alpha, which is the manifestation of torque, but rather the rate of change of angular momentum. Because when you put a torque on something, you're going to increase its angular momentum. This is very much like how force is the rate of change of linear momentum, but it's much more important in rotational dynamics. So we're going to give it some more attention here. We can think about how hard we're pushing on something by the rate of change of its momentum. We can substitute it in, pull out the m, and we have m dv dt, which is force is equal to ma Newton's second law. But we can turn this around and solve for the impulse, the change of momentum that we give something, and it's just force times delta t. And if force is not a constant, then it's not just force times time, but it's the integration of force over time. So if you put a force on an object, imagine yourself in space, no friction, and you can find a way to put a force on a large object. The momentum that you give it is going to be the force times the amount of time. So you're pushing on it, and it's getting more and more momentum as you push on it more and more for a longer period of time. That's the impulse, or its change of momentum. So similarly, well, we know that torque is equal to the angular acceleration times the moment of inertia. We're going to try to express torque in terms of rate of change of angular momentum. Then the impulse, your change of angular momentum, would be equal to torque times change in time. And so we can think of something that has a lot of angular momentum, like a space station rotating in space. Well, how did it get that angular momentum? We had to put a torque on it, maybe with rockets, over a period of time. If the torque changes in time, this product needs to be expressed as an integration. We integrate the torque over time, and it gains angular momentum in that process. This is where we get our two momentum conservation laws. If force is the rate of change of momentum, then if force is zero, there can be no change in momentum, and momentum is constant if outside forces equal zero. So no outside forces from a system, the momentum of that system must be constant. Similarly, if torque is the rate of change of angular momentum, your change of angular momentum is the integration of torque times time. And so change of angular momentum must be zero. Momentum is a constant if external torque is equal to zero. So you have a system there, it's going to maintain its angular momentum, always the same, unless you put in an outside torque, which will introduce this change of angular momentum.
I want this, but I get this.
So I asked my sensei how to do a wheel kick. And he says, a wheel kick requires some time. In fact, it requires some time times torque in order to get that angular momentum.
In a wheel kick, you are rotating and there's angular momentum because your body has a large moment of inertia with your feet so far from the central axis. If you are spinning very fast, you have much angular momentum. You start out with no angular momentum, and then when you want to throw your wheel kick, you need much angular momentum. That change in momentum comes from the torque you provide times the amount of time you are giving that torque. And so, how do you get torque? Torque is radius cross force. So here's your body, your feet are a certain distance apart. And there's a force put on your body by pushing on the ground. You push on the ground, you have that force, that gives you a torque in this direction. You must do that for a long time in order to get all that angular momentum so that you can throw an effective, very fast wheel kick. Because once that foot leaves the ground, radius is zero, and your torque goes to zero. So you need to get all your angular momentum before that foot leaves the ground. And therefore, the feet must stay on the ground as long as possible.
Okay, so let's take a look at my wheel kick. How am I doing with angular momentum? So I've just begun to turn. I haven't turned very far and I'm not turning very fast, and I've already picked my foot up. So I've only applied torque to my body for a short period of time. I have very small angular momentum. I'm not spinning very fast, as you can see. Okay, what can I learn from my sensei? He begins his kick, rotating his shoulders with both feet on the ground. With his arms outstretched, he's putting a lot of angular momentum into his upper body. Okay, he's fully twisted and turning fast before, and he's looking at this direction. So he's put a lot of angular momentum in his body in the upward direction, rotating, before he lifts his foot off. Okay, can I learn a wheel kick? The key is to keep your feet on the ground until you actually see the target. That will guarantee that you're providing torque for long enough to get enough angular momentum in order to have a fast kick. So here I start my kick. I'm rotating my arms outstretched with my feet on the ground. And I'm in full rotation of my upper body before my leg comes off the ground, and I can already see the target.
Once the external torques are zero, you can actually add angular momentum to your lower body by twisting your upper body in the opposite direction.
You can see this concept very nicely with his roundhouse kick demonstration. He's going to kick with his rear foot. It's going to come around and kick from the side. So his foot's rising, his body's turning with angular momentum in a downward direction. Watch what happens to this arm as his leg comes up. His upper body then begins rotating in the upward direction, which imparts even more angular momentum to his lower body. Again. Lastly, I rotate my shoulders back the other way so that as much angular momentum as possible goes into this leg. So I'm all excited to try out my wheel kick. But Sensei says we should not start fights. But we should really never start a fight with a wheel kick. But you know, as a physicist, I have to find these things out for myself. It's a lovely wheel kick. I mean, what could go wrong? Well, let's see. It takes a long time for me to gain this angular momentum. It's also going to take a long time to get rid of it. Sensei sees I'm gaining angular momentum with the torque I'm applying to my upper body. And he knows that I'm going to continue turning in this direction, so whatever is coming at him from this side. I cannot charge forward, and he knows I'm not attacking forward, so he doesn't even have to run away. He just needs to lean back. So he's not hit by my foot. And he knows now I can't stop turning, because in order to change my angular momentum back to zero, I need to apply a lot of torque. And I can't do that because I have only one foot on the ground. So he knows I will continue turning. My leg is passed and he is safe to step in. Oh, a spear poke to the neck. Very bad for me. And then some overacting. And some overacting. And some overacting. So in summary, torque is the rate of change of angular momentum. Thus, a change of angular momentum is the integral of the torque you put on a body over the time. If you want to change your angular momentum, if you want to gain angular momentum or lose it, you need torque over time. And so if there is no torque, then there's no change of angular momentum, and angular momentum is conserved. Also, angular momentum and change of angular momentum is a vector. So if there's no outside torques and your angular momentum must be conserved, if one part of your body gains angular momentum in one direction, the other part of your body must gain angular momentum in the other direction.